about how these monomers are linked together. How do we form these covalent bonds? There are two processes in terms of forming and breaking these various saccharide bonds. So condensation is the first mechanism. This is when we join two monomers together and we release water. This is what helps to form that bond. In the example here, we have glucose joining with fructose, and then the end result is to form sucrose by way of condensation, the release of water, and the formation of the covalent bond. The opposite of that is hydrolysis. Hydrolysis is inserting water, and the insertion of that water molecule helps to split or cleave this covalent bond, and then that can give us our two monomers on the other end. So this is a bidirectional sort of reaction where condensation makes a saccharide, hydrolysis splits a saccharide, and then we can have water either being added or released as a result. Okay, let's shift gears and think about lipids here for a minute. So what I began describing earlier is the way that our various atoms combined together in different proportions gives us different basically elements or different molecules that are going to behave and look differently depending on how those atoms are combined. So there's a lot of hydrogen and carbon atoms mainly forming lipids, right? There's not oxygen involved. And because of that, we can describe lipids as being nonpolar. They don't interact very well with water. They don't form bonds in general very well, right? As we described earlier, this is because of oxygen's makeup. Oxygen is going to form bonds very easily, very nicely. It's going to be partially charged. So there's going to be a little bit of positive excess in one area of the molecule, a little bit of one area of the atom, excuse me, and a little bit of negative in another area. So that allows oxygen to form bonds easily with other atoms. And because we don't have a lot of oxygen here, we see that lipids are really sort of, I like to think of them being introverts, right? They don't like to interact very well, especially not with water. And so this is what we mean by being nonpolar or being hydrophobic. Hydro meaning water, phobic meaning a fear of. And so that is the kind of oil and water analogy that we can typically see. There are 5 classes of lipids. There are triglycerides, which we know are pretty common in our diet, and this is one of the ways that we store fats and lipids in the body. There are ketones, and ketones can be an alternate storage of fats, an alternate storage of energy. There are phospholipids, which are really important in our cell membranes, the phospholipid bilayer that separates our various fluid compartments. And then there are eicosanoids and steroids. Both of those are involved in hormones, in signaling molecules, and we'll talk about how those are very, very useful in the body as well. So we'll look at each of these classes of fats and look at how they differ structurally, and functionally. Let's begin with triglycerides. So triglycerides is comprised of a glycerol sort of backbone, which is this portion of the molecule. Right, this is our glycerol backbone, and then it has 3 fatty acid tails, so to speak, attached. So this is what a triglyceride looks like. And the fatty acids, if we look at them in more depth, they're basically carbon chains, right? There's chains of carbons attached to each other, forming this carbohydrate tail. Now, the way that these tails are formed will give us bigger functional properties of our triglyceride. Example, we can have a saturated fatty acid, which simply means that there are no double bonds involved. It's all single bonds from one carbon to the next, and there's no double bonds included in this chain, in this fatty acids chain. Versus unsaturated fatty acids, which means that they're not fully saturated. We could, in fact, make additional carbon bonds or carbon chains attached because we do have a double bond involved in this chain. So this is a saturated fatty acid, and this is an unsaturated fatty acid. Now, we can think about dividing these even further. If we look at unsaturated fatty acids, they can be divided into trans fatty acid, which is where the double bond has hydrogen bound to it on the same face of the chain, right? This is a cis fatty acid is where they have those hydrogens on the same face versus a trans just meaning different or opposite. And these hydrogen bonds are bound on opposite faces of our double bond, okay? So cis fatty acid, unsaturated, versus a trans fatty acid, unsaturated. And I want to point out here that the same elements or compounds are involved. The exact same elements are involved. However, we have different functional properties simply because of the face on which these are bound on one, the cis fatty acid, versus the other, the trans fatty acid. Now, functionally, we can think about our saturated fatty acids as being healthy. So these types of fats that exist in our diet are much more healthy, much better for the heart and for our vascular system than these types of unsaturated fatty acids, right? Unsaturated fatty acids are healthy, saturated fatty acids are unhealthy. Okay, my apologies. Versus trans and cis, another kind of division here. Trans unsaturated fatty acids are unhealthy. Cis unsaturated fatty acids are slightly healthier. So the same compounds coming together, if they are structurally organized in a different way, they can give entirely different functional properties, as we see with saturated, bad for your health, unsaturated, slightly better for your health. Okay. Let's talk about ketones here. So ketones are basically another type of storage of fat. They become extremely important in diabetics or people who are on low carbohydrate diets, the so-called keto diet. And the way that we make ketones is to cleave or hydrolyze triglycerides, and then we can free up those fatty acids, and then they can be shuttled off to the liver where they can be converted to these ketones, okay? The way that we get major ketone production in our body is either if we're not having access to glucose, which is a diabetic or someone who has insulin resistance, where that insulin is not giving the correct instructions to allow glucose to be liberated, or someone who is intentionally withdrawing or withholding glucose in their diet, which is a low carbohydrate diet. And so you're not having access to glucose. So what do? You take your fat, you shuttle it off to the liver, you make it into ketones, and then you can have access to those ketone bodies to generate energy, sort of a backdoor pathway to making energy. Now, the reason that this is so useful in terms of diet culture these days is that this allows your body to tap into fats during periods where glucose is not available, right? If you withhold that glucose, you can kind of force your body to start breaking down its fats so that you can use that as energy instead. The detriment with this is what we call ketoacidosis. And this becomes important in diabetics who are not intentionally trying to withhold their glucose, but they just sort of happen to be in that state. This builds up ketones in your blood, and that can lead to comatose states. This also presents with acetone breath, which is that kind of metallic breath or sometimes metallic taste in your mouth. And so that is kind of the importance and the clinical relevance and background of ketones. At the bottom here, we can see two different types of ketone structures. So the acetoacetic acid is an example of what this ketone would look like. But really, we can replace these R groups or these functional groups with any different composition of functional groups to make many different types of ketones. Okay, but this is the general makeup of our ketone structure.